Hey everyone, and welcome back for another deep dive. Today, we're going to be tackling disjoint sets.
Oh, yeah.
It's a pretty fundamental concept in computer science.
Yeah.
Um, you sent over some research papers and lecture notes, and I have to admit, when I first looked at this, I thought, oh, this is going to be a tough one. But, once you break it down, it's actually pretty cool.
Yeah.
So disjoint sets, they're all about organizing stuff into groups, but with one very important rule. No overlaps.
Right.
Like imagine you have a bunch of objects. Could be anything, really.
Okay.
Numbers, letters, people, you name it. And you want to put them into groups where there's no overlap between those groups. That's the essence of disjoint sets.
You know what's so fascinating about disjoint sets? They seem really simple at first.
Yeah.
But they're so powerful when you actually put them into practice.
Yeah, like a Swiss Army knife for coding.
Exactly. Like you got all these tools ready to go.
Right. And like any good tool, there are different ways to implement them, each with its own pros and cons.
Absolutely.
And that's what we're going to be unpacking today on this deep dive.
Yeah. By the end, you'll be able to pick the right tool for the job.
Exactly like a pro. So let's start with the basics here.
All right.
We have three main operations that we can perform on disjoint sets: make set, find set, and union.
Right.
Make set is pretty straightforward.
Yeah.
You're basically creating a new set with just one element. It's like starting a brand new group, and this one item is the first member.
Makes sense.
Then you have find set, which is like asking, hey, which group does this element belong to?
Right.
So it helps you find the representative of that set, the element that speaks for the whole group.
Like a spokesperson.
Yeah. And then finally there's union, and this is where the real action happens.
Okay.
You're merging two separate sets together. They become one big happy family.
I like to think of it like building with Legos.
Okay, I like that.
So make set is like grabbing a single brick. Find set is figuring out what structure that brick belongs to, and union is snapping two structures together.
Oh, that's a really good analogy.
Right.
Yeah, it makes it so much easier to picture.
Visualize it.
So now that we got the basic actions down, let's talk about how we actually represent these sets in code.
Okay.
Our sources dive into three main approaches: arrays, linked lists, and trees.
Right.
Starting with arrays, they're kind of like having a bunch of numbered storage bins. Each element gets its own bin, and inside that bin, you store a pointer that tells you who the representative of the set is.
Right, so it's like a directory.
Yeah, exactly. And arrays are a great starting point because they're easy to visualize and work with. Make set and find set are super fast with arrays.
Yeah.
You just go directly to the bin you need.
Okay, to the index.
But where things get a little tricky is with the union operation.
Okay, why is that?
Well, if you're merging two large sets that are represented as arrays, you might have to go through and update a lot of those pointers.
Oh, I see.
And that can take a while.
Yeah, that makes sense.
It's like having to rearrange a ton of boxes in your attic every time you want to combine two collections.
Oh, yeah, that would be a pain.
Yeah, not the most efficient process.
So what about linked lists? How do those work?
Yeah, so linked lists offer a different approach.
Okay.
Think of each set as like a chain, where each link represents an element, and the first link is like the designated representative.
Okay.
Merging two sets then becomes super simple. You just attach one chain to the end of the other.
Oh, okay.
It's a much smoother process than shuffling around elements in an array.
I see that.
But our sources mention a cool trick to make this even faster.
Oh, what's that?
It's called the weighted union heuristic.
Weighted union heuristic.
Yeah, have you heard of that?
I have, but I'm not sure I totally get it.
Okay, so it's like being a strategic Lego builder.
Okay, I like that.
Instead of just randomly attaching chains together,
Yeah.
you always add the shorter chain to the longer one.
Oh, that's smart.
Yeah, it keeps the overall length of your chains as short as possible,
Yeah.
which speeds up future operations.
So it's like picking the shortest checkout line at the grocery store.
Exactly. You got it.
Okay.
But now let's talk about the big kahuna of disjoint set representations.
Okay, hit me with it.
Trees.
Trees.
Our sources seem to agree that this is the most popular approach,
Yeah.
but they can be a bit harder to wrap your head around at first.
Yeah, I can see that.
Like imagine a family tree
Okay.
where everyone points upwards to their parent. The root of the tree, the ancestor at the very top, becomes the representative of the set.
Right.
So to merge two sets represented as trees, you just attach the root of one tree to the other.
Makes sense.
Sounds simple enough, but our sources warn that if we're not careful, these trees can get really tall,
Oh, yeah, that's right.
making it slow to find the representative.
Right, because you'd have to go through more nodes.
Exactly, and that's where some seriously clever optimizations come in.
Oh, this is getting good.
Path compression and union by rank.
I've heard of those.
They're all about keeping our trees short and tidy so we can find what we need quickly.
I can't wait to learn more about those.
Me too.
Yeah.
I think things are about to get even more interesting, so let's dive into those optimizations after a quick break.
Sounds good. So path compression and union by rank, those are the optimizations we were talking about before the break.
Yeah, you know me, I love a good efficiency hack.
Right.
So tell me, how do these things actually work?
Okay, well, let's start with path compression.
Great.
It's like taking a shortcut through a dense forest.
Oh, yeah.
Imagine you're searching for the representative element in a tree, and you got to traverse this long path from some node all the way to the root. Path compression basically says, hey, why walk that whole path over and over again?
Right.
Let's just make a direct link from that node straight to the root.
So it's like updating your family tree so everyone reports directly to the head honcho.
Exactly.
I can see how that would save some time.
And the best part is you can actually do this as you're performing a find set operation.
Oh, so you're not only finding the representative, but also optimizing the tree along the way.
Exactly. Two birds, one stone.
Oh, I love it. Okay, so that's path compression. But what about union by rank? How does that work?
All right, so union by rank is all about keeping our trees short and sweet.
Okay.
Remember, the taller the tree, the longer it takes to find the representative.
Right.
So when we merge two trees using union by rank, we always attach the shorter one to the root of the taller one.
It's like stacking blocks. You always put the smaller one on top of the bigger one.
Exactly. You want a nice, stable tower.
Makes sense.
And here's the really cool part.
Okay.
When you combine path compression and union by rank, you get algorithms that are crazy efficient.
Oh, really? Like, how efficient are we talking?
We're talking near constant time complexity for both find set and union operations.
Wait, hold on. Constant time complexity. Doesn't that mean it takes the same amount of time no matter how big the set is?
Pretty much, yeah.
How is that even possible?
It's like magic, right?
Yeah.
But it all comes down to the interplay between path compression and union by rank. Path compression is like flattening the tree, and union by rank prevents it from getting too tall in the first place.
So they work together to keep things running smoothly.
Exactly, a true dynamic duo.
You mentioned something called the inverse Ackermann function earlier.
Yeah.
Our sources say it has something to do with the efficiency of these algorithms. But I gotta be honest, it sounds kind of intimidating.
The inverse Ackermann function, it's a mouthful, I know.
Yeah. You break it down for me?
Well, it's one of those things that gets computer scientists all excited.
Okay.
It's a function that grows so slowly that for any practical problem you'll ever encounter, it's basically a constant value.
So even though a single find set operation might take logarithmic time in the worst case scenario,
Right.
when you factor in path compression, the average time, or what we call the amortized cost, becomes practically constant.
Exactly. It's like saying you might lose your keys every once in a while, but on average, you're pretty good at finding them.
That's a good way to put it.
And that's why disjoint sets with these optimizations are such a powerful tool. They let us do set operations really, really fast, even when we're dealing with massive amounts of data.
It's amazing how something that seemed so abstract at first can have such a big impact on performance.
It's like finding out that a tiny change to your morning routine can save you hours each week.
I like that analogy.
Right. Small changes, big results.
So we've gone from theoretical concepts to practical applications.
And the applications are everywhere.
Yeah, like what? Give me some examples.
Okay, well, remember that example we talked about with the cities and the roads?
Yeah.
That's just the tip of the iceberg.
Okay.
Disjoint sets are used in all sorts of things, from social networks to financial analysis to image processing.
Okay, so we've gone from organizing Legos to optimizing Google Maps.
Pretty much.
Yeah, that's pretty impressive.
And we're just getting started. There are so many applications out there just waiting for someone to use the power of disjoint sets.
I'm ready to dive in.
All right, well, before we go too far, let's take a minute to review what we've learned so far and then wrap things up with some food for thought.
All right, so we're back for the final part of our deep dive into disjoint sets. This has been a really interesting conversation.
Yeah, it's amazing how such a simple idea can lead to such powerful algorithms.
Totally. So let's do a quick recap of what we've learned about disjoint sets.
Okay.
First, we talked about the three basic operations: make set, find set, and union.
Right, those are like the foundation of everything we do with disjoint sets.
And then we talked about how to actually represent those sets in code.
With arrays, linked lists, entries.
Right, and we saw how each representation has its own pros and cons. But trees seem to be the most popular choice.
Yeah, because they can be really efficient, especially when you use those optimizations we talked about.
Right, path compression and union by rank, those are the real secret sauce.
They make our algorithms super fast, even when we're dealing with tons of data.
And let's not forget about that inverse Ackermann function.
Oh, yeah, that thing is wild. It grows so slowly that it's basically a constant.
It's like the tortoise of the function world.
Haha, yeah, exactly.
So we've covered the what and the how of disjoint sets.
Right.
But now I want to talk about the why.
The why.
Yeah, like why should we care about this stuff? What kind of problems can we actually solve using disjoint sets?
Well, that's the exciting part. There are so many applications for disjoint sets.
Okay, give me some examples.
All right, well, we already talked about finding the fastest route in Google Maps and grouping pixels together in image segmentation.
Right. And you mentioned social networks and financial analysis.
Oh, yeah, those are great examples too.
Can you elaborate on those a bit?
Sure, so let's say you're looking at a social network like Facebook.
Okay.
Each user is an element, and each friendship connection is a link between those elements.
Mm-hmm.
We can use disjoint sets to figure out if two users are connected through a chain of friends, kind of like figuring out degrees of separation.
Oh, so if I want to know if I'm connected to like a celebrity on Facebook.
Exactly. Disjoint sets could help you figure that out.
That's really cool.
And in finance, you can use disjoint sets to analyze transactions and detect potential fraud.
How does that work?
Well, think of each bank account as an element.
Okay.
By tracking how money flows between accounts, we can use disjoint sets to find clusters of accounts that are linked together, and that can help us spot suspicious activity.
It's incredible how something as abstract as disjoint sets can have such real-world implications.
It's like a secret weapon for solving all sorts of problems.
I love it. So as we wrap up our deep dive into disjoint sets,
Yeah.
what's the one key takeaway you want our listeners to walk away with?
I'd say keep an eye out for opportunities to use disjoint sets in your own work or studies.
Okay.
You might be surprised at how many different areas they can be applied to.
Great advice. Well, that concludes our deep dive into the fascinating world of disjoint sets.
Thanks for having me.
It's been a pleasure chatting with you. We hope you enjoyed this episode and learned something new along the way. Until next time, keep exploring, keep learning, and keep those knowledge fires burning.